weight to press it down. Okay, and then that in that case it might keep the same size. However, that means the material will have a lot of stress inside the material, so that stress will have to go somewhere. So sooner or later it would break down.
Okay.
But overall, I would say it has to be design will have to be increased. The problem is in what dimension.
Yes, very good. Oh, okay, so we go back to Professor of Mechanics. Somehow you haven't been able to convince all of them. I don't know why. So the answer is. What do you mean?
Okay, I fully agree with Professor there. If let's say we don't have the plate at all, if you don't have the plate at all, you just draw a line, a circle on the plate, and you hit the plate. Will the circle become bigger or become smaller? Imagine that is the situation. That means it's totally a metallic plate. Okay. Now we just draw a line on it, and then you just observe the line of this, the diameter of the circle. Okay. No hole. Will it become bigger or become smaller? It become bigger, right? That is, I think everybody agree with that, right? After cutting the hole, after cutting it becomes smaller. Does it make sense? This is a layman thinking. Okay, another way of thinking is this. If you draw small little circle here, okay, all right. Okay, now as Professor has said, after you hit, every one of them become bigger, 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 bigger. Okay, so now they all stretch with each other, but they have to tie with each other. So when you push it, it has to push this way out. Okay, all have to push this way out. Okay? Because the plate becomes bigger. Okay, remember, the plate becomes bigger. Okay, so this is another way of looking at it. I hope it makes sense. Maybe Helene can further expand on it.
No, I wouldn't further expand on that because you're all the professors. But it is the answer is that it will become bigger. Okay, and the mechanics professor has explained it very well. The point is here, the concept question is to test the concept behind the phenomena that we are observing. Okay, so the phenomena that we observed here, can I have my slides back? The phenomena we observed here is that, we think is bigger. Even if we say it's smaller, the question to your students is, what is the reason? What is the concept underpinning the answer? Now, if the concept is consistent with known concept, this is what we think it is, fine. But if the concept, that their explanation comes to you and says, no, 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 I think it's something else, that's where, as the professor, you can now understand their thinking behind the question that you're asking or the answer that they are giving you. So this is what concept questions are about. Concept questions test the student's understanding of a concept that you are teaching them. Okay? But we don't test it directly. Do you know this concept that things expand, when you hit them? We're not testing that. But we're showing them a phenomena. In this case, things expand. And then we're testing the concept by throwing a little bit of twist to it. I'm drawing a hole now in the center. I'm cutting a hole. Is your concept, understanding of the concept, able to explain the observation or explain your answer? Okay? Whichever it is, whether it's 1 or 2 or 3, then you, as the professor, will have to make the decision. When they explain to you, does it make sense? Yeah? And I feel that this is a wonderful way to surface students' thinking, understanding, and misunderstanding of the concepts that you are trying to teach. Okay? So this is what concept questions are about. Yeah, Christian? Yeah.
Does this understanding of the concept for the concept question just mean understanding?
Here is they are able to apply the concept. The understanding here is
So
an application.
cover the whole range of
Yes, that's right. So they're able to explain to you what the concept is and apply it to this situation, explain it within this context, like he did. The whole will increase because the concept underpinning that is them. So they're able to explain, they're able to apply it to this situation and explain it to you. It's deeper, really
So
deeper.
it goes like from the they can recite, they can explain, they can apply to the simple situation. But it's true that this concept question is not designed to extract the ability to synthesis, analysis.
It depends on your question. This is a very simple one. So if you put in a more high level that requires them to make judgment and to tell you on what basis I'm making this judgment, okay, yes, then that's the concept. So it depends on the question that you put up there. Okay, but the idea here is that we want to test their understanding, to check that they understand the concept that we're teaching them. Yes, I think you came in a bit late. They were explaining to each other why, trying to convince each other my answer is right or my answer is wrong. Yes, we spent some time on that. Yes, you are right.
Sorry, I mean, how can you feedback to the students?
How can you feedback? Okay.
I think Berlin is using this example to illustrate the concept that we want the student to learn actively. We were observing everybody was really very active just now. Okay, so that is the point that we're trying to arrive at. We want how to get students to learn in an active manner. First, they try to internalize their own thinking and then try to convince the other. And after convincing each other, between two of you, you try to convince the whole class. So there's a lot of activity, active learning involved in this whole process. So that was the point that we tried to arrive at. Active learning can be done in this manner.
Sorry.
Okay, any other questions?
Actually, when you say this kind of concept question, actually in physics we have what we call thought experiment. Means that you set up the rules, you set up the criteria, and then try to use that rules, try to use that criteria that you have set up, and apply it to the question at hand. And if it explains what you think very well, then perhaps your idea, your rules, your setup is correct. However, if by using your setup, your rules, your criteria you use, and then you turn out that you come into the different conclusion, then there might be something wrong in your idea. So that means by these kind of things, you don't need to go into the calculation or anything. You just follow the rules and see if it comes to the contradict result compared with what you have in the first place. And by that, you might apply that to one question and then apply it again to the different question. If they come to the same reasonable, logical solution, in a way, okay, now your rules, your setup are at least correct for these two problems. It might not be correct for another one, but that means there might be some other exception that you have to look at. Problem is, sometimes by using this kind of thought experiment, at first it might seem to be logical, but once you try to explain it to someone else, you come into yourself, you come into the conclusion that, well, my thought at first might not be correct, because you now, because of you trying to convince everyone else, it turned out that you actually contradict yourself. So you have to go back and change the rule in the first place. I mean, as long as we accept that we might not be correct, and we can change the ground rules. I mean, not only the student, the professor himself can come to the better, come to the deeper understanding of the problem in the beginning.
Fantastic. I think that's one of the slides I have. Let me just go forward a bit. Where's my slide? Here. Okay, so I don't know whether you've seen this before, but what you just showed is this, that if you have to explain it to someone else, the likelihood of you remembering the concept, the idea, the reasoning is higher than if only you were to just read it or hear about it or just see it. So what you just shared is exactly what we're trying to get at. Okay? So we all know metals expand, etc. But now you have to talk to someone and tell someone, hey, yeah, I know it expands, but why it expands? Okay, now you're using what we call the language of your profession, your discipline. I have to use the terms, like what you said. Sorry, so you have to use the terms, you have to use the equations, you have to use the principles to explain to someone, oh yeah, it expands and it's because it's this, etc., etc. Yeah? You have to use the theories. And that's where you start to remember it better. Okay? Rather than I stand there and tell you all this, it just goes in, I hear it, but I only remember about 20% of what I hear. But if I have to explain, and as he says, then you start to question yourself, do I really know what I'm talking about? Yeah? Do I really know? He's really confident, he knows. But I'm sure all of you in your undergrad studies would have come across this before, somewhere or other. This explanation before. Yeah. So what he said was totally right. And the focus, as what TY says, is to get students engaged in learning, engaged in explaining. As you said, Bloom's taxonomy, yeah, engaged in justifying my answer, convince someone about it. Okay, I want to show you this video. TY, can you just click the video on the video? This is by Eric Mazur. Eric Mazur, he's a physics professor at Harvard. So if you're going to the MIT conference, he will be there. He's one of the keynote speakers. I hope, yes. Yeah. Oh, I need the sound. Is there sound? Sound? Oh, okay. You have to increase my volume. No volume. That's my job. The next one.
Professor Mazur developed a learn basic concepts far better than before. Requiring students to read, think, and reflect before the lecture is the first step in Professor Mazur's interactive process. He also uses the course website to monitor their learning and communicate with his students.
I don't go into the classroom lecturing on what I think they need. No, they tell me what it is that they want me to cover.
It was helpful for Professor Mazur to answer those questions that we had. And sometimes, like, it didn't feel embarrassing at all if he addressed your specific question because the whole thing was anonymous.
So the idea is to teach by questioning rather than telling. I will talk a few minutes and then put on the overhead projector a question. And then I tell them, take a minute to think about it. They think about it. And after they've thought about it, I need to get some feedback on their answers. So turn to your neighbor and see if you can convince one another of the correct choice.
Right, it goes out of the page and on the top goes in, so
Right.
they cancel each other out. There is a torque. There is a torque.
How do you know that? And B is down, so the force at the bottom would be clockwise. And in a sense, this process, this engagement, this teaching by questioning rather than by telling, forces students to develop these models in the classroom.
I think the lectures were really good, and it worked out really well, the idea of everyone teaching each other.
And we soon realized that, yes, we were picking up the material faster than we had in the previous physics course that we had all taken.
You can forget facts, but you cannot forget understanding. And that's actually exactly what I would like to achieve here. I want them to understand the subject so that they know it for the rest of their life.
So sometimes people ask me, hey, can we do this in lectures? I heard your lectures about 40 students. I think it can be done. Yeah, it will take a bit of time, but the understanding is deeper. Yeah, okay, let's move on. So concept questions, or using the questions, can be used in lecture-based courses to check students' understanding. Okay, it will reveal the difficulties with key concepts that you are trying to teach them and to get them to know and understand and use. Okay, the idea is to focus on one concept at a time and to give them several plausible answers so that the students can surface their misunderstanding. And that's where you can address what they understand or don't understand. Okay? Are not solvable by relying solely on equations. So these are like what was the professor there pointed out. There's more to it. It's not just equations. You don't need equations. You need understanding of the concept to answer the question. And you prove it with equations, by solving equations. Yeah? And well, we wanted to show you this, but I don't think we have time, that you can actually use, he used clickers. Yeah, do you all have clickers here? Oh, you do? Okay. Oh, right. You have to draw it out for the students, yeah. But my colleague was actually sharing with us a poll. Do you remember what it was about? Yeah, anyway, this is something that you can download.
You go into this particular website, okay, and then of course you have to pay the license. Okay, they charge a very small fees for 50 license or 100 license, about maybe for 100 license about 2,000 Sing per year. Okay, and once you have the license, you just go to this particular website, you just key in the questions, and everybody in the audience, as long as they have internet access, just log into here, either with the iPad or iPhone or the notebook, log inside there. The question, when you log inside here, they will ask you for a number to key in. So as long as you give in the number, that number corresponds to your session, okay? And then the question will automatically appear on the notebook or the iPhone. And then there will be a multiple choice question corresponding to your question, and you just have to put in one A, B, C, or D, just like the previous question there is. And then after everybody have key in, straight away, let's say this is a question, straight away the response will come up. Okay?